In the beginning there was nothing but this, and this is energy momentum tensor. There was no space-time, only this. And this is same as this, which is the curvature of space-time. In other words, this is the absence of space-time. These two are the same thing. Now this is all the thing that the universe is made up of. So this was the situation at the beginning. So at first the balance of the universe was tilted towards left, in which there is more of energy momentum, there is more of space-time curvature, and more of the absence of space-time itself. And so on the right hand side there is less of space-time itself. And the confinement represented by del x was maximum and momentum was maximum. And on the other hand, on the right hand side, the space-time itself was very limited, which is represented by the Minkowski space-time or metric tensor. Then something started happening because of the quantum uncertainties and quantum fluctuations. And so the curvature of space-time or energy momentum started converting to space-time or flat space-time. And so we have this little bit of balance. So we have more of space-time now and less of the curvature of space-time and less of the energy and momentum in the universe. And so the confinement is decreasing and momentum is decreasing. And then we have, this is the future of the universe, where you will see the confinement represented by del x is minimum and momentum is minimum, and so we have more of flat space-time or space-time and less of the curvature of space-time and less of energy and momentum. The greatest thing Einstein did was to unify the fundamental aspects of reality. And this equation, that is Einstein's field equation, is the representation of that unification. So what are the fundamental aspects of reality? They are nothing but energy, momentum, mass, and space-time itself. So Einstein unified the concepts like energy, momentum, mass in his special theory of relativity on the one hand, and on the other hand he also unified space and time itself. But to unify energy, momentum, matter and space-time, again the greatest unification was done through the theory of general relativity. And this is the equation of general relativity. So on the one hand is the special theory of relativity unified energy, momentum, mass, and the same special theory of relativity unified space and time. But to unify these both into unified theory, general relativity had to be introduced. And that is what this equation represents. Now, in this equation, the left hand side is all about curvature or dent in space-time, and this lambda thing is about the expansion of space-time itself, in particular the accelerated expansion of universe, and in other words that is dark energy. And the right hand side is about energy and momentum or matter equivalently. So if you just simplify this equation by getting rid of this lambda term or absorbing this into g mu nu, we get this. So we could just absorb this lambda thing into g and this becomes this fat g. So this is our equation, which is, now if you just work out, now if we take a look at this constant 8 pi g by c power 4, g is like at the order of 10 to the power minus 11, whereas c power 4 is in the order of 10 to the power 33, and 8 pi can be neglected. So work out this constant term, this just adds up to something like 10 to the power 44, which is something like c to the power 5.2 or c to the power 5, where c is the speed of light, of course, and g is gravitational constant discovered by Newton. Now some might say that because the value of g is very weak, that is why gravity is weak. But that is the observation, that is the fact, that is not the answer to the question why gravity is weak. And just like what gravity is and how it really works, was the entire mechanism was given by Einstein through his general theory of relativity. tells us why gravity is weak. So what Newton discovered the value of g was just an observation, but general relativity provides an answer to why the value of g or why gravity is so weak. Now, if we just work out that equation, we get this, which if you compare, which can be written as this, and so this is something like E is equals to mc square, but the order or magnitude is much higher because c to the power 5 is way bigger than c to the power 2, and it is way bigger. So 10 to the power 25 is something like, if you can imagine a kilometer, then 10 to the power 25 kilometer would be something like 100 times the diameter of the universe itself. So that is how big 10 to the power 25 is. So 10 to the power 25 kilometer is like 100 universes. So anyway, we have this new and more unified version of E is equals to mc square, where space-time, energy, momentum, where all the fundamental aspects of reality is brought under one umbrella of general relativity, the theory of general relativity. And so if you see this equation, you can see on the left hand side we have energy, momentum, and on the right hand side we have the space-time curvature. So just like in case of E is equals to mc square, a unit amount of mass, a unit mass, if you convert into energy, gives you an enormous amount of energy, which is to the power of 10 to the power 16, right? So if you convert a small dent in space-time or a small curvature in space-time, you'll get about 10 to the power 44 orders of energy. That is a huge number, and that number is of the order of 10 to the power 25 times greater than what E is equals to mc square stands for. So you see, if you convert a small curvature of space-time into energy and momentum, you will get a huge amount of energy and momentum, far more than what you would get by converting a single unit of mass. So if you do this thing in reverse, you would require a huge amount of energy or energy density to create a small dent in the fabric of the cosmos, in the fabric of space-time. So to create this curvature, you'd require enormous amount of energy, and that energy is huge. Now, because gravity is nothing but the curvature or dent in the space-time or the fabric of the cosmos itself, so gravitational strength is nothing but the strength of the curvature of space-time, or the strength of this dent, or the amount or the magnitude of the dent that you create in the fabric of reality itself. Now to create this dent, you will require a huge amount of energy given by the order of 10 to the power 5. This is like 10 to the power 44. There is a large amount of energy, and so space-time, it seems, is the hardest thing to mold. So if you are talking about some elements, well, what would be the hardest element? Now space-time is way harder and harder and harder than any element, and other fields like electromagnetic field and other fields can be easily molded or can be easily excited, but to create a dent in space-time, the fabric of cosmos itself, you'd require huge amounts of energy, and because that dent curvature is the gravity itself and the strength of gravity, you would require huge amount of energy to create gravity. And that is why gravity is so weak, because with even huge amount of energy you would only be able to create a small dent or a small gravitational strength.